Welcome, everybody. How about a trip to the moon or Mars? NASA has plans to reach both, and there will be boatloads of sensors on board. We're talking today with NASA's Dr. Kathleen Boggs about what tech we will need for NASA's upcoming human missions, starting with Artemis going to the moon. Artemis, by the way, was the twin sister of Apollo and the goddess of the moon in Greek mythology. The space capsule going to the moon will look something like the older Apollo capsule, but it will be named Artemis. So, hi, Katie. What can you tell us about Artemis and your fascinating role at NASA?
Hi, Matt. Well, first of all, I want to say thank you for having me here at the Sensors Conference. I think this is a really fantastic opportunity to talk to folks who are going to help us with these missions. Artemis is actually a program. It's a series of missions that have the goal of expanding human presence beyond Earth. There's just so much behind that, though, because, I mean, you could say, hey, Apollo expanded human presence beyond Earth. But we're going further than that. We know so much more about the moon now than we did back in the 70s. And, you know, at that time, we thought that the moon was barren and that it, didn't have any water or anything like that. And now we know, and in fact, we just announced about a week ago that we have discovered not only that there was water at the moon that we knew about in craters, but that it's everywhere. And so the science that we're going to get to do is incredible. And really, even in addition to that, we're going there to help to develop our technologies and to really, make the humans spread out further into the solar system and make it even possible to do that. So I have a couple of slides here that kind of introduce what Artemis is. And I won't spend a lot of time on these, but the first mission is really going to be us testing out our spacecraft. So we are building the Orion crew capsule and the Space Launch System, because the first thing we need is a very, very big rocket. And so we will, in the first couple missions, test that out, make sure we can get to the moon with it, make sure we can orbit the moon. And then we're also going to launch a Gateway, which is a spaceship orbiting the moon. And then we will build up a human landing system, and we will conduct that first moon landing of the Artemis program using the human landing system. And we'll also, at the same time, if you look at this chart at the bottom, you see all these little robots. Well, we're also doing some science demonstrations there and some technology demonstrations. And those are going to be delivered by the commercial lunar payload services, which is different this time because that is actually NASA purchasing delivery to the moon as a service. You'll see here that space station that you see in the top part starts getting more and more complicated as we will eventually start conducting landings via the Gateway. So the Orion capsule and human landing systems will connect to the Gateway, and we will actually pass through the Gateway on our way to the lunar surface. At the same time, we're building up habitats and rovers and more robotic missions. And so you'll see there's kind of this base camp building up beyond the 2024 return to the moon. Now, I think this is all very exciting, and I think it's because exploration is written into our DNA. We really strive to figure out what's out there that we don't know as human beings. Okay, so Matt, you asked what specifically my role is with all this. So doing all these different things, these different missions we have going to the lunar surface really is going to require new capabilities that we didn't have before. So my job is to look at what we can do now and what we need to be able to do and to understand the gap between those things. At NASA, we really, really like to focus on technology. I mean, there's so many engineers and scientists, and technology captures our imagination. But I actually like to step back and focus on the overall capability because I want to describe what the problem is rather than focusing on the solution, because that stifles innovation. So we're really looking to describe the problem so someone can either propose a technology to close it or even a different way of operating or a different mission profile entirely. So we look at that and prioritize among the different gaps and things we need to do and then try to feed it into NASA's budget process so that we can fund the things that will actually enable us to go to the moon and even further.
Wow. It's a big deal, no question. So is NASA on track for putting the first woman and the next man on the moon by 2024 or thereabouts?
Yeah, from a technical perspective, we are. The thing that's challenging is actually maintaining the budget and the schedule to do so. So we're really hoping that we get the funding we need so we can pay our bills and our spacecrafts and supporting systems get built. So yeah, I'd say from technically we're on track. We're just hoping to keep the budget pressure on.
And the elections won't sidetrack that, or do you have any thoughts?
Yeah, so right now, and this is recorded, so we don't actually know the result of the election right now. But NASA historically has really enjoyed support from both sides of the aisle. And personally, I'm really optimistic that we'll be still talking about lunar exploration once the results are known.
Well, good. So how is the moon mission different from the last time we went up there and other missions?
Yeah, so I think the main difference is the purpose. Apollo was mostly a geopolitical driver for it, and there's still some of that now. But now a lot of the people who were our adversaries during the Cold War are actually our partners on this.
Right.
And yeah, it's just incredible, right? And even at the International Space Station, I mean, the Cold War was fought against the Russians, and now we work with them every day on the space station. And going forward, building on a lot of those partnerships that we started with the International Space Station. And really the science that we want to pursue and the pursuit of knowledge is much different now because of what we know about the moon. And then finally, I mentioned earlier the commercial lunar payload services. That's really completely different. The fact that we're going with contractors providing directly. So during Apollo, there was something like 375,000 contractors directly supporting the program. And NASA will rely on contractors in that same way for a lot of this. But also being able to deliver research capabilities to the surface via commercial providers, similar to how we're delivering cargo to the International Space Station, is a big change. And so it'll be robots and humans working together to explore the moon this time.
That's huge. So what capabilities are we going to need to get there? Or maybe, as you said it, what problems do we face? What tech do we need that we don't have?
Yeah, so at a high level, I mean, we need a heavy lift capability, which means a big rocket. We need habitation systems to keep the crew safe and healthy, mobility systems to help us move around on the surface and do the science. We need new spacesuits that actually work on the surface because the International Space Station ones are not meant for walking. And we need the communications and the power infrastructure to support all of this. In all of those cases, the moon is a really harsh environment. Big difference being the radiation. So International Space Station does have some radiation, but we're largely protected by the Earth's magnetosphere. And the Gateway and the moon have a much higher presence of space radiation. So our electronics and our humans have to be able to survive that. And then moon surface is dusty. One of the lessons learned from Apollo, and that's also what's different here, is we're able to build upon those lessons from that set of missions. So the lunar surface is very dusty. The dust is highly abrasive. And so we need technology to help us keep dust off of parts like solar arrays. We need to keep it out of seals and any mechanical parts that could wear. So that's a big challenge for us. And while we're at the moon, the types of science we want to do are challenging. Scientists would love to go into what we call permanently shadowed regions, which are areas that, well, they're permanently shadowed. They don't get sun, so they don't have heat and they don't have light. So we'll need technologies that will allow us to go further into those. And some of those PSRs, to use our acronym, have steep sides. They're craters. And so we need mobility systems that not only can survive in that really cold environment and the dust, but then also operate on a steep slope. So the more we can do those things, the more science we can get. So there's some really tough challenges there driven by the kinds of science that the researchers want to do.
But not so tough that they can't be overcome, I guess.
No, not so tough. And the fact that there's abundant water, or at least enough water outside of those permanently shadowed regions now to study, actually even changes that. So we're really looking at where we want to go and what specific experiments we want to do while we're there.
This one, the Artemis lands on the South Pole, I think.
Yes. So we are targeting a South Pole site. The specific site has not been chosen yet. I think you'll be hearing a lot more about that in the next couple of years.
Okay, wow. So tell me about some cool new sensors that we're going to need. I mean, I guess this goes all the way down to the IC level, the integrated circuit level.
Yeah, so it's interesting. We're going to need a lot of things, like I said, that can survive the radiation, the cold environments. We also need things that can support autonomy. So the gateway, which I mentioned, that's orbiting at the moon, is actually not continuously crewed, right? So instead of having people there who are there to fix it, to move things around, to do the science, a lot of that's going to be done autonomously. So sensors that can support understanding the situation, we call it situation and self-awareness of the gateway systems, are going to be important. That goes through all the vehicle systems. And some of the science systems. Some science is actually better done without human beings present. So we'll need to be able to manage that science autonomously. And it's great because, I mean, in ISS, the humans are always there. So you can't do that science at ISS. So that's a definite set of sensors related to understanding what state everything's in. Is it healthy? How are we operating it? Also, but speaking of humans, we need to be able to, for long duration missions, to be able to do some in situ diagnosis and even treatment. Now, at the moon, we can bring people home within a few days if there is an issue, but even determining, hey, is that just indigestion or are you having appendicitis, right? You need something that will help you understand what's happening. So we've looked a little bit at ultrasound, and what's interesting about ultrasound in space is that because you're floating, your organs are in different places. So it's not so simple to just like tell the computer to find the organ, because the human being's attitude compared to the sensor matters.
I think I saw a movie once where the astronaut actually did take out his own appendix, but maybe you won't be doing that. So.
Well, I think it was The Martian, and he removed a piece of an antenna from his belly. But yeah, that was it. You would have to have some emergency medical treatment, initial triage, and diagnosis tools. So that's a whole suite of specialized sensors related to people. And then for the science, we obviously need sensors to detect the water, to detect chemicals that are there. We're worried about volatiles, which are chemicals that like off gas from the moon. And then potentially microbes, understanding whether humans are actually off-gassing Earth microbes from their spacesuit matters when we go eventually to Mars. So we want to study that while the humans are actually exhaling the way they would during a mission where they're walking.
And
so
the inverse is true, bringing it back home, I assume.
Yeah, that would be bad too. That's a different problem, sort of more around how do you, if you want to bring a sample home, how do you encapsulate it, both to protect the sample and preserve that sample, but also if we were bringing a sample from Mars, which we would like to do, you want to make sure that you don't somehow like let a microbe like slip out if there are microbes. We don't even know that right now. So it's a problem of monitoring that sample container, which again could be a sensor issue.
Yeah, and I guess you're going to be doing the sensor like we do in industry, where you're looking for breakdown of parts and predictions, like whether the toilet's going out and stuff like that.
Yeah, so it's funny you mentioned the toilet. Yes, we are, in fact, we're doing sensors like that. We know that there's parts of the toilet that actually get hot when they're going to fail. And so we're building thermocouples in there to measure the temperature and help us predict. that those things are happening. Also, there's some thought that for long duration habitats that might be on the lunar surface, it would be good to have an idea of the structural integrity. So there's talk of putting maybe embedded sensors in those, and so you can monitor what's happening there. Particularly if it's a situation where it's dormant, you don't have the crew going, "Hey, there's a problem here." You know, you need that. So
there are earthquakes on the moon, right?
I am not a fan
on parts. And
yeah, so we do use seismic sensors. There's a sensor right now on Mars actually called the Mole, and we like literally dropped it down a hole to measure that kind of stuff. So there could be some use for that to understand what's going on. And there's also some different sensors related to. They're talking about, they think you can get a record of the sun from the moon because they think there's layers of dust and stuff on it that have been injected and all that flowing across the solar system and deposited on the moon. So there may be some need for some in situ analysis related to that.
Wow. So this kind of boggles the mind when you think about it. So can you just tell me, for people who may not know, I mean, radiation just basically could destroy human tissue. Isn't that the essential concern?
Yeah, well, my understanding, and I'm not a medical doctor, but my understanding of the risk as we're tracking it right now, it's more about a long-term cancer risk. So you build up those radiation effects through time in space. And so it's like cumulative radiation exposure that matters. We worry about it more on a Mars trip than on a lunar one because Mars is like a 3-year mission. We might be able to get it down to 2, but basically 2 to 3 years in that deep space environment. And it's not in that case while you're on the Martian surface. Mars has a little bit of an atmosphere that protects you. It's the transit between. So the moon is a great opportunity for us to study ways to shield against that. And then there's something called galactic cosmic rays, which we aren't even sure how they're going to impact the humans. I've heard some thoughts about neurological effects and psychological effects, but that's a big unknown right now.
I think I read or saw a movie where the spaceship to Mars was shielded from radiation with a layer of water. And then they had to drill in to use the water to drink because their water supply purification system failed, turning urine into water. Anyway, I just had to throw that one in there.
And that's actually something we've talked about is we would use what we call water walls. The challenge with water is that it's very heavy. And like right now we're working to recycle 98% of the water. Astronauts like to say, yesterday's coffee is today's coffee, because we recycle a large amount of the water and we're pushing that even further. So I don't know that we would tap into water walls to drink. I think that would be, but you might recycle it the other way, right? Like turn today's coffee into tomorrow's radiation protection. So yeah, there is stuff that has been looked at. It's a balance between how much water you have to take and how much you can make and how much you can recycle. And we have people who do some really detailed simulations to figure those things out.
Yeah, wow. So talking about Mars, I mean, is it too early to talk about a Mars timetable? I mean, there's a lot of things that have to happen by 2024 and then right after that. So, I mean, what would it be?
Right now, it's a little too soon to put like a date on it. Now, we have been directed there's something called Space Policy Directive 1. Folks can Google it. It says that NASA should lead the return of humans to the moon for long-term exploration, followed by human missions to Mars and other destinations. So we are directed to consider Mars in our planning. And really, as we're developing systems for the moon, we have Mars in mind all the time. Both from the standpoint of, are there opportunities to test things there that we would do at Mars to understand maybe how you might conduct like a science mission on Mars using humans and robots together. And then it's also to gain time on systems. So yeah, you just want to get comfortable. You know, we're like, even human beings on Earth right now aren't comfortable fully with autonomous vehicles. And so imagine now we want to be comfortable with an autonomous vehicle away from Earth with our best and brightest people in it. And so that gives us time to gain that comfort and to buy down the risk for doing that much farther from home.
Oh, wow. But so I think that whole question of autonomy and maybe artificial intelligence is going to play a lot into a big long mission like that. I mean, are you guys doing your own direct research into AI, or I mean, you
And
must do some,
we
but
are. Yeah, we are. We also have a system where we look at other people's AI and test it out for space applications. And so, yeah, AI definitely is going to become important, particularly when we go to Mars. The as I think most people learned in The Martian, there's like a 20 odd minute communications delay, which really, you know, for nominal situations, you can deal with that fairly well with humans. But if something goes a little bit wrong, right now, you know, you get a leak on the space station, and someone on the ground immediately figures out, like, is this something that's important that I need to wake the crew up for, or can this wait? So some of that initial triage would have to happen on the vehicle, and AI would be great for that. Also for helping, you know, the crew troubleshoot problems. And so there's things there that AI will definitely support. I think also there's some potential applications in science. You know, some science data processing would probably be useful. Have to probably talk to my friends about that, but I know there's more look at that in the science community. So yeah, AI is definitely part of it, and testing out some of that AI at the moon is going to be important for us.
yeah, sort of just on the AI track for a second. I mean, the big advance with modern chipsets is that people can put a processor right next to a sensor.
Mm-hmm.
You know, that's sort of the edge concept, and then, you know, that's actually avoiding, you know, some big data center back wherever in the center of the ship or back on another orbiting body or the Earth. So
Mm-hmm.
I guess, you know, that seems like, you know, that's all just going to kind of, maybe the timing is just perfect, you know, to come together for the use of I mean, and you would have to train the data sets, right? I mean, that's how AI works. It works on the basis of, we know what 30,000 lung patients or cancer patients look like, so we can say what, you know, what it looks like in you. I mean, that's machine
Yeah.
learning, but I mean, so that concept is going to definitely have to play out, maybe with the experience on the moon.
Yeah, some of that will contribute. I also think as AI advances and we move beyond machine learning, there will definitely be other applications to that, because you're right, we don't have large data sets for human spaceflight. We have even like human health, which is challenging. I mean, our data set for human health effects in space is small, so it's kind of difficult to even think about how you might diagnose things that could be impacted by gravity or lack thereof. But yeah, so that's part of the reason why building up at the moon will be important. And I agree, we're at a great time. AI has exploded. I think I read somewhere the worldwide investment in AI is actually bigger than our entire annual human spaceflight budget. So I'm excited because I think there's going to be some good things that come out of that we can incorporate into our missions that will make some of these deep space things really happen in our lifetime.
Yeah, so I guess as a final question, I'd just like to raise the sort of concern that some people raise, that why are we spending money on this kind of thing versus, you know, the Earth habitat, global warming, I don't know, fighting viruses on Earth. What's your response to that?
Well, I think investment in space is investment in all those things. You know, we have turned great climate research out of the International Space Station. Some of the stuff that we're doing to recycle water on the space station and now for deep space missions is directly applicable to Earth. There's numerous spin-offs, and ultimately an investment in deep space exploration is an investment in science. So I don't think it's an either or. I think you get both out of this.
Well, that was well done. Sounds like you've spoken to a few committees, maybe. All right.
Yeah. I hope, I mean, I hope people agree with me. I think this is a important investment, and I understand like COVID relief and everything else is important too. But we get great medical research out of this as well.
Wow. Well, thank you, Katie, for this amazing insight. Really appreciate it.
Thank you for having me. I really appreciate being here. Thank you.